In this video, we're going to walk through how to determine electron configurations in orbital diagrams. And I really think of these as the same thing, just represented in a different way with different types of information emphasized. An electron configuration is going to be a string of the orbitals and the number of electrons in them written out in a line, whereas an orbital diagram will take that information and represent it with an energy axis to show visually the relative energy levels and where those electrons are. So the information contained in them is the same, and it's just kind of a different way of viewing and presenting the information. So I want to talk first about how to decide what ground state electron configurations are. And this ground state word is new here. We haven't really talked about this, but we have talked about how electrons can be excited and then relax to a lower energy level. So when an electron is excited by absorbing energy, it's first at the ground state. So this is like the initial state before it becomes excited. Another way to think about this is kind of like the atom status quo. It's the state of the atom when it's in its lowest energy configuration. And so to develop these and decide how electrons will be arranged within the atom, we're going to follow a couple of rules to help us do that. The Authbao Principle, Pauli exclusion, and Hund's rule. So let's walk through those. The Authbao Principle states that we will fill energy levels with electrons from the lowest to the highest. So that means we will always fill n equals 1, and then 2, and then 3, because electrons are always going to prefer to be in its lowest possible energy state. That's the most stable, right? It's the most attraction to the nucleus, which is a stabilizing force. So then from the different n levels within the types of orbitals, we'll always fill the s orbitals first because they're lower in energy than the p or the d or the f. And so we'll always go in that order, s to p to d to f, in the order that we fill these. Except, of course, when we have this situation where our d orbitals are actually higher in energy than an s orbital. And so we'll always go for the lowest energy. And that's going to give us that pattern that happens once we hit the n equals 3 level, where our order goes, 3s, 3p, and then 4s before we do 3d. And then it goes 4p, and then 5s, 4d, etc. Our next rule for determining these electron configurations in orbital diagrams is the Pauli exclusion rule, which means that we can't put more than 2 electrons per orbital. Then we lead into Hund's rule, which is that when we fill these orbitals with electrons and decide where they go, we first make sure that we put 1 electron in each orbital that's degenerate, which means to have the same energy level. And only after we've placed 1 in each of these energy levels at the same energy do we go up and pair electrons up and put 2 in. So here on the side, I'll show you with a piece of an orbital diagram. If I had 4 electrons that I was going to pair or add to our 2p orbitals, I would not start pairing them up right away at all. Instead, what we always do for Hund's rule is we put in 1 electron in each of our 2p orbitals. These are the only ones that are at this energy level, right? And then I come back and then I start pairing them up. So I'd have 2 unpaired and then 1 orbital that had a pair of electrons in it with 4 electrons. And so when we represent these as electron configurations, they're going to look like this, a string of numbers and orbitals with the number of electrons in them as a superscript. And we can write these in a couple of different ways in terms of the way we order it. And so for the lower energy levels where we don't have the d electrons, so 1 and 2 energy levels, that it's straightforward. We go s and then p. So we have 1s1, then 2s2, and 2p6, right? We're just going up in energy. Then we come to the 3rd energy level, and that's where we're going to introduce our d electrons. And so we'll go 3s2, 3p6, and then here we have a choice. We can either put 3d10 next, and have all of our N energy levels in the same kind of clump, and then our 4s2, or we can do this based on the energy of each one. And we know that the 4s orbitals are lower in energy than the 3d because they penetrate in towards the nucleus more and have less shielding from other electrons, so feel a stronger net effective nuclear charge or effective nuclear charge. So you can do this either way. That's fine. I personally will always write the s orbitals before the d orbitals because that's easier for me to remember the order for the energy, and it's just a habit that I have. But there's a great point to be made for always having everything in the same N energy level together in your electron configuration, because it's easier to see where your valence electrons are, which we'll talk about later. So up to you. So the order of this will always be the same. You'll notice that our s orbitals always have 2 electrons in them if they're filled. Our p orbitals always have 6 if they're filled, and our d orbitals always have 10 if they're filled. If we get to f orbitals, they will always have 14 if they're completely filled. So something like 4f14. And the f orbitals only occur at the n equals 4 energy level and higher. So we won't see that in 1, 2, or 3. So the next thing that we can do is show an abbreviated electron configuration. So this is our abbreviated. So if strontium has 38 electrons, I write out my electron configuration. My total number of electrons will end at 5s2. After I fill that, I'll have 38 total. I can abbreviate this because it's a long thing to write by using the nearest but smaller noble gas and say, you know what, just assume a noble gas configuration. And then beyond that, you would add 2 electrons, and that would give you strontium. And so this is a way of kind of truncating what can sometimes be a really long electron configuration. Now let's look at what strontium would look like in a orbital diagram. So an orbital diagram will be exactly like our electron configuration, except it's going to actually show the energy levels relative to each other on an energy scale. And so we have energy here on our scale. And this is the order that we'll always present them in. It's the same no matter what. 1s, 2s, 2p, 3s, 3p, 4s, 3d, and so on. So if I have strontium, I'm going to fill in 38 electrons. So I'm going to start at the bottom, and I'm always going to half fill an orbital first, and then come in and double it up with 2 electrons. And then once I have 2 electrons in it, I move on. So that's 2, 4. Now I go into the 2p, so I half fill. And then I come in and I add in my second electron. So I'm now at 10 electrons, 11, 12, 13, 14, 15, 16, 17, 18. Now I go to the 2s, or 4s is the next one. And then I fill the 3D. And that's going to be 1 electron in each of those 5 orbitals. And then I start pairing them up. And I'm going until I've added 38 electrons. After the 3D, it's the 4p orbitals. And now I'm at 36 electrons. So I need just 2 more. I've got 1, that gets me to 37, and then 38. And so my orbital diagram would look like this, and it shows the electrons, how they're paired, and where they are relative to one another in energy. So let's do another example to see how this looks. Let's do sodium and then arsenic. And so if you would like to go ahead and pause the video and try this for yourself, please do. And so I'm going to write out the electron configuration, and I'm also going to write out the orbital diagram, and I'm going to use this as a kind of a template. So the place to start with these types of problems is with the periodic table and identify the number of electrons that we have in our element. So for sodium, it has an atomic number of 11, and so it'll have 11 electrons. Arsenic has an atomic number of 33, so it has 33 electrons. So let's start with sodium. So sodium's orbital I'll do the orbital diagram, then the electron configuration for sodium, and then I'll flip the order for arsenic. So if I have 11, I'm just going to count them out as I follow my rules for filling electrons in my orbital diagram. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so this is what my orbital diagram looks like. It looks like I fill up to the the 3s orbital. So if I'm going to write that out as an electron configuration, I'm going to write 1s, 2, because in the 1s orbital, I have 2 electrons, 2s2, 2p6, and 3s1. Now, if I want to do the abbreviated, I would try to find the closest noble gas. And sodium is in that third period and in the first group. So in the second period of the periodic table, in the noble gas column, which is 18 or 8 if the A for the main groups, it's neon. And so I can abbreviate this with a symbol in brackets for neon, saying assume neon's electron configuration and then add 1 3s1 electron to get the sodium. All right, now I'm going to switch colors and I'm going to do arsenic. Okay, so let's do the electron configuration first. I'm going to need 33 electrons. And looking at my periodic table, arsenic is in group 4. I'm sorry, it's in group 5A, but it's, or 15, it's in period 4. So that means it's going to go up to that N equals 4 energy level. So I can see that my noble gas that's closest to arsenic but smaller is argon. And so if I wanted to, going backwards all the way, I would say, all right, well, I know I need to have the same electron configuration as the noble gas argon and build from that. So after argon has a filled N equals 3 orbital, it goes down to the 4s2, and that's followed by the 3d10, followed by 4p3. So if I wanted to write this all out, instead of the abbreviated version, I would start at 1s2, 2s2, 2p6, 3s2, 3p6, and now I'm at argon's electron configuration, so I keep going, 4s2, 3d10, and 4p3. All right, now I could build my electron config or my orbital diagram. I'm just going to layer it on top of the sodium one, if you don't mind, and it'll be in different colors. So I'm going to start and I'm going to count up to 33. So I've got 1 and 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 29, 30. It's a lot of fun to listen to me count, I'm sure. And then we go 31, 32, 33. There we go. We've got 4p3 for our final one. And the thing that really strikes me about the difference in information that we have in an orbital diagram versus an electron configuration is that this 4p3 right here tells me I have 3 electrons in my p orbitals. And when I look at it here in my orbital diagram, it's very clear to me that all of those electrons are not spin paired with another electron, that it's just 1 electron per orbital per orientation of an orbital.